Alright guys, this is another video, and again, if you didn't see this video posted this week or the other week that the day I told you guys I'm gonna be posting the video, it's probably because of some technical issues, or I've probably deleted some clips. So we have to go. So we're gonna be treating down below. So furthermore, let's not waste any of our times. Today, guys, this is a topic we're gonna be talking about: elasticity. So this is a very interesting topic because it's basically on physics. So how can we define elasticity? I don't want to waste anybody's time. Just gonna go before I go into the definition. This video I'm just gonna be going into the definition of elasticity, giving you some terms, giving you some graphing points, and also straight going to be doing some calculations. So now let's go into LM. How can we define elasticity? Okay, elasticity can be defined as the elastic as the density of any material, or can be this density of any material, or can be defined as the or can be defined as an elastic material. And elastic can be defined as an elastic material whereby the elastic material has the ability to regain its original size, length, and also its size, length, and original shapes. So all things are down to down basic definition of elasticity. If you guys can't understand my own terms, I'm going to leave another term of the definition of elasticity above above the top, so you can see it over there. So now let's go into terms using the elasticity. We have basically many terms in using elasticity, and basically some of those terms are the deforming force, the perfect elasticity. We have the perfect elasticity. We have the perfect plastic body, and we also have the tensile stress, strain, and also tensile strain. So moving forward, so we also have okay, let's you define some two things under the terms using elasticity. So we have the deforming force. I'm going to leave it up below. You can see the terms using the basically terms used in elasticity, and I want you guys to read them in your textbooks. So let's go into deforming force. For example, deforming force. This is the ability. This can be defined as a type of force whereby it's being applied to change the configuration of any material, of an elastic material. For example, let's use the typical iron. The melting point of iron is above us there. So the typical iron. It, so let's use the typical iron. For example, now when the iron is heated, it can able to bend and also change its configuration. So that's under the iron. We also have the perfect elasticity, that's the rubber. When it's being stretched, you can see if the rubber is being stretched, it's expands, and it's can the rubber also has elastic limits. But when the rubber you stretch the rubber, it's a perfect elastic because it can also regain its original sharpness and shapes and size. So moving that forward, so we also have some, okay, we have the tensor strain and tensor stress. The tensor stress, for example, let's use the typical tensor stress. So we under the tensor stress, they have the formulas. So let's go into the formulas above us. You can see the two formulas of the tensor stress and the tensor strain above us. This is the formula for calculating for the tensor stress, and this is also the formula for calculating for the tensor strain. You can see the two down below above us. So let's go into the next topic. So the next topic is going to be on Hooke's law. So probably some of you all know the definition of Hooke's law because it's very simple. Because Hooke's law, it's very simple to understand how we can define Hooke's law. It's very easy to explain Hooke's law. So let's go into the definition of Hooke's law. Hooke's law can be defined as provided that the elastic limit of an elastic material doesn't exceed the force applied to the material. So that's basically the normal definition of Hooke's law. So for example, now let's go into this. So a rubber, a typical rubber. Let's go back to rubber. Where if the rubber exceeds its limits, it's what happens to rubber. The rubber can easily break. So, provided I'll show you the graph above us, you can see they can be also be labeled in letters or alphabetical numbers. So you can see the labeling where they have their own different parts and points of its elastic limits. We have the ABCD according to put as that. So the D part is also known as the breaking point, and that's whereby the rubber has reached and exceeded its elastic limit. So moving forward, we have done on the calculation. We've gone. We just want to make it very simple, and you can see the two graph down below above us. So If you have any forward question, leave it down on the comment section. I'm going to be enable the comment section down below because I forgot to enable the former comment section in my introduction to the channel. So I'm going to be enabling the comment. I'm going to be enable the comment section down below so you guys can comment and problems you don't understand, some topics parts you don't understand in elasticity, and you guys can also give me some question that you think that's somehow difficult to you. Maybe in the future video, I'm gonna give you guys some credit and also help you guys in future video. So let's go into some calculation. So we have some basic calculation on how to calculate on Hooke's law. So let's go into typical questions first. All right, guys. Before I start the calculation, so I have under the topic I mentioned the tensor stress and tensor strain, the formula above us. You can see them over there. So it also have its own typical formula. That's Young modulus. That's Young modulus equals to tensor stress over tensor strain. So I just want you guys to keep that in the mind because okay, I'm gonna leave the formula above us here. You can see the formula there. So I just want to keep it there because we're gonna be coming across some few questions that's gonna be treating on Young modulus. So I just want to tell you guys now. So let's go into typical question. And before we start under Hooke's law, remember the Hooke's law whereby the elastic mean of an elastic material doesn't exceed its force applied before. If it exceeds its force applied, this is going to break. The elastic material is going to break. So it also have its typical formula. That is the equation or formula for solving for Hooke's law. That is F equals to Ke. That is the F is known as the F is known as the force. The K is known as the constants, and the E is known as the elasticity. In some textbooks, it can also be seen as this. You can see I'll leave it down there. In some textbooks, it can be seen the formula can be seen as this. So yeah, let's go into some typical solvings. Let's try this question out. A force of 1.8 newtons extends a wire by 0.4 centimeters. What will extend the wire by 1.25 centimeters if the elastic limit is not exceeded? So it's a very typical question. So let's write it down first. So solution. I want my camera to be. So solution for the question. So we have the F. That's the writing of the equation. That's solution number 1. We have the F K E. The F is known as the force. Remember, and yeah. So the force is given to us as what? The force is given to us as 1.8 newtons, and the extended wire, that's E, is given to us as 0.4 centimeters. So yeah, I was going to do solvents. So now remember, okay, let's go. So we're looking for the constants. Remember, we're given the force and the extension, but we weren't given the constant. So the force was given to us as 1.8, and we weren't given the constant, so we give the constant as nothing. The elasticity was given to us as E, and the E was given to us as 0.4. So how can we get rid of this? In the future video, I'm gonna teach us on changing the formula. So just leave them that. So how can we take this off the K? So we're gonna divide both sides so we can let the K stand on its own. So that's 0.4 divided by 0.4. So this that's K equals to 1.4. So that will give us 4.5 newtons per meter square. So before I go, K, the constant, can also be measured in newtons per meter square. So as we've already calculated for our constants, now we can move to the other part of the question. So the other part of the question says, what force will extend the wire by 1.8 centimeters? So we're given the force, but the question says what force will extend the wire by 1.25 centimeters. So we go into the solvents. So the force is unknown, but the extension was given to us as 1.25 centimeters. So that and that, then use the constant because we're looking for the force. That's using Hooke's law again. That's Hooke's law. That's given to us as. So we're going to multiply 4.5 multiplied by the extended. That's 1.25 centimeters. So that's F. That's 4 multiplied by 1.8 centimeters. That's 4 multiplied by 1.25. That will give us our final answer is 5.625 newtons. That's our final answer. Alright, that's how to solve for Hooke's law. So we're going to move to the other part of the question. The next question is the extension in a spring when 5 grams was hung from it. and was 0.56 centimeters, or something around 0.56 centimeters. If Hooke's law is obeyed, what is the extension caused by the load of 20 grams? So it's a typical solving. So if you guys should try the question down below before I start. You can pause the video if you want. If you want to pause the video, you can pause the video and try the question out. And I'm going to solve it now. Let's start. All right. So let's start with the question. So the question that says the force is given to us. The force is given to us, right? And the extension is given to us, and we in typical Hooke's law states that F is directly proportional. So let's go. So we use Hooke's law formula. So the force is given to us as the force is given to us. The force is given to us as okay. The force is also measured in grams, so the force is given to us as 5 grams. 5, and the constants, we're given the constants, so we're going to be looking at the constants first. So let's go into the if it's hung from 0.25, so 0.56. So how can we get this rate of this? So we're going to get it by dividing both sides. That's 0.56. Then this cut this. Then we give it 5. Let me make it clearer. So this is 0.56. So we're going to divide both sides. So that will give us the constant will give us 8.9. Sorry about my handwriting. So that will give us 8.9 per meter squared. Yeah. So we're giving it for the. So the question is common says in some part. So if Hooke's law is obeyed, what will be the extension caused by load of 20 grams? So, but we're given for the elasticity, for the the extension, but we're giving for the if Hooke's law was obeyed, that's the force. So we're giving for the force. The force was given to us as 20 grams, and the constant we already solved for the constant. That's giving us newtons per meter squared. So how can we go for this part? So then we go into the typical solving. So yeah, and then so we then go in typical Hooke's law. That's 20 equals to that's giving us K. That's 8.9 newtons per meter. We're giving for the E, so we keep the E like this. This is the E. So we're going to divide both sides by 8.9. So that's newtons per meter. That will give us, sorry about that. So that will give us the extension equals to 20 divided by 8.9. So when we calculate on that, that's 20 divided by 8.9. And that will give us our answer as 2.247 or 2.25. So anyways, this will be our extension caused by 20 grams. So yeah, this is our final answer. If you got the answer down below, please leave it in the comment section below. If this was your answer, please leave it in the comment section down below. I'm gonna give you credit for that. So let's go into the next question. So the next question is a bit tricky, so let's go into the solvings. So the next question says a 10-gram mass placed on the pan, a 10-gram mass placed on the pan of a spring of a spiral balance causes an extension of 5 centimeters. If a 15-gram mass is placed on the pan of the same spring balance, the extension is what? So this one is a bit tricky, but still simple. So I'm gonna try solving it. Pause the video if you want and try solving it, and leave your answer in the comment section below. Now let's go into the solving. So a mass is placed. So the solution. So we're given typical formula. Let's go with the typical formula. That's F equals to K. That's a constant over elasticity. So the force is given to us as 10, and where we're given the elasticity, we weren't given the elasticity, but we're given the extension. So the extension is given to us as 5. So typical, we're gonna divide through by 5 because we want to make 5 for the constant, and the constant is given to us as 2 newtons per meter squared. So we go into the other part of the question. The other part of the question then says, if a 15-gram mass is placed on the pan, so the force is given to us, but the extension wasn't given to us. So the extension wasn't given to us, but we got our constant as 2. So how can we solve for it? So we use Hooke's law formula again. So the Hooke's law formula is 15 gram and the k is given to us as 2, but when given for e, so we're going to divide through by both sides so we can find for the extension. So if we divide through by both sides, that's 2 divided by 15, so that will give us e equals to 7.5 centimeters. 7.5 centimeters. That is our final answer. If you know your answer was this 7.5, please let me know in the comment section below. I'm gonna give you some. I'm gonna give you guys some free credit for that, and I'm gonna give you guys a shout out. So let's go into the next question. This we're gonna make a typical. So the next question then says. Okay, the next question then says is on a Hooke's law, by the way. The next question then says a load of 20 newtons on a wire of a cross-sectional area of 8 multiplied by 7 raised to the power of 7 meters squared produces an extension of 1.10 raised to the power of 4 meters. Calculate Young modulus of the material of the wire if the length is 3 meters. So this one is pretty simple, and we can basically solve for it. So how can we solve for the question? So remember Young modulus. Remember, I'm gonna leave the Young modulus as m ym. So formula for calculating for the Young modulus is tensile stress over tensile strain. That is the formula for calculating for Young modulus. So for tensile stress, the formula for I told you guys in the comment. I told you guys in the beginning. So in some part, I told you guys the formula for calculating for Young modulus. So we then go into the tensile stress formula for that's F over A over E over L. So yeah, this is the typical formula. Yeah, just let me set close bar for you guys. It's the typical formula. Yeah, for calculating for Young modulus. So the question, the cross-sectional area, so the F, that's the force. The force was given to us as 20 newtons divided by 8.10 8 multiplied by 10 raised to the power of 7. So we're calculating for the tensile stress. So the final answer for tensile stress, that's 20 divided by 8 raised to the power. And that is okay. So yeah, this is there. So that is 25. Tell. Yep. All right. Let's round it off. So that'll give us 2.5 multiplied by 10 raised to the power of -7. That is the final answer for tensile stress. That's tensile stress. So we move it into tensile strain. So tensile strain. So that's formula. That's elasticity. The extension was given to us in the question. The extension was given to us as 1.5. That's 1.10. 1 multiplied by 10 raised to the power of 4 and divided by 3. That's loaded. So we divide through by that. So our answer will give us that. And that will give us our tensile strain as 3 multiplied by 10 raised to the power of 4. So this is our final answer. So remember the true formula of calculating for Young modulus. That's Young modulus we'll be getting our answer. That's 2.5 multiplied by 10 raised to the power of 7 divided by 3 multiplied by 10 raised to the power of 4. So how can we solve for this? So then you go into this as, so we're going to open the bracket as 2.5 multiplied by, we're going to multiply by 3, close the brackets. Then remember for the formula, the law of indices, that's 10. That's multiplied by 10, law of indices. That's -7, -4. That's -7 and -4. So if that's giving us negative, that's 2.5 multiplied by 3. That'll give us 7.5 multiplied by 10. That's negative. This and this, that will give us -11. So our final answer will be 7.5 multiplied by 10, -11. That's our final answer. If you got this as your final answer, please let me know in the comment section down below, and I'm going to be enabling the comment section. So let me know in the comment section down below, please. Yes, please let me know. I'm going to also give you guys some credits and a shout out. Let's go. So yeah, And you guys can also take this question and try it out. Try this question out and leave your answer in the comment section down below. I will, because the question is above us, as you can see the question. Please don't forget to subscribe and use the form method I taught you guys, and use us to try out this question I'm going to leave in here. So please don't forget to subscribe. Thanks for watching my video. Yeah, please don't forget to subscribe. Peace out. Thank you guys. Hope you enjoyed the video, and hope you also learned some few things on the elasticity, because it's just a short topic on basically me explaining a short topic on elasticity. Please don't forget to subscribe, please. Yeah, peace out. Bye guys, and wish you the best. Bye.